Hello and welcome back to C++ Under the Microscope. My name is Sam and today we're dissecting floating-point numbers. They look like decimals, but the CPU stores them in binary scientific notation. We use Compiler Explorer to see exactly how the CPU moves these bits around. Why, for example, 0.1 plus 0.2 doesn't equal 0.3, and what the hidden bit actually means. A 32-bit float is split into three parts: the sign, that's 1 bit, exponent, 8 bits, and the Mantissa, 23 bits. Let's look at our first program. We use std_bitcast, that's the C++20 way to say take these bits and interpret them as a different type without any conversion. This is how we get the bits. Basically, we say with bitcast, take the bit pattern of whatever f is and cast it to unsigned integer, but don't convert it, meaning keep the bits as they are. This way we get the sign. We have the bits here. We shift them by 31 bits and apply this mask. This way we have the most significant bit, which is the sign bit, move to the least significant place, and this way we can extract what it is actually. In floating-point numbers, the sign is obviously either 0 or 1 for negative or positive number. That's the exponent. It is 8 bits. So what do we do with it? We take the bits and we shift them 23 bits. That's the Mantissa size. So basically we remove the Mantissa and then we apply this mask, which is 2 bytes worth of ones. And this is how we extract the Mantissa. We take the bits from here and we apply this mask. This mask is actually the number 23. This way we keep only the Mantissa, the rest is set to 0. Now the next is to print all these different components of the floating point. Right? The next thing is to use that function. So this is the example. What we see for 2.0, the sign is 0, which means that the number is positive. Exponent is 128. Mantissa is all zeros. And what we see for 0.1, again the sign is 0, which means it's positive. Exponent is 123 and the Mantissa is some number. In hex representation, we can see that 2.0 is this number in hexadecimal, and for 0.1 is this number. Now for 2.0, the exponent is 128, and according to the floating-point standard, it uses a bias of 127. So the actual exponent is stored exponent minus bias, and that results in real exponent. So in our example, 128 minus 127, that means 1. And therefore the calculation of the formula, of the floating-point formula, is as follows: 1.0 multiplied by 2 to the power of 1, and that equals to 2.0. For 0.1, we have a stored exponent of 123, so that is 123 minus 127, and that equals to minus 4. So we're looking at something multiplied by 2 to the power of minus 4. The bias lets the CPU store both positive and negative exponent without using a separate bit sign. So let's talk about the hidden bit. Let's look at 2.0 example. Its Mantissa is all zeros. And if the Mantissa is 0, how do we get that 1.0 multiplied by 2 to the power of 1 example? Where does that 1.0 comes from? And here comes the hidden bit. in the 14-point standard, it assumes that every normal number starts with the leading 1, this here, before the binary point. We don't store that bit, and that's why it's called hidden. So the actual value is as follows. We have -1 to the power of the sign multiplied by 1 plus Mantissa, that's divided by 2 to the power of 23. Now that's done because this is in binary and it needs to represent values between 0 and 1. And that's why we divide it by this number. It's a scaling thing, basically. And after that, we multiply by 2 to the power of the exponent minus the bias, which is 127. And this is the formula for so-called normal numbers. And so if we apply this to our example 2.0 here, we get -1 to the power of the sign. This is 0, that's 1, multiplied by 1 plus our Mantissa is 0, divided by 2 to the power 23 plus 1, this will be 1.0, and we multiply by 2 to the power of the exponent, which is 128 minus 127, that's 1, so 2 to the power of 1, which is 2, and we get 2.0. That's how we get this number. For 0.1, the Mantissa represents a fraction that, when added to 1 and multiplied by 2 to the power of -4, it gives approximately 0.1. So if you apply the formula, it will be something like this. 1 to the power of the sign in our example is 0, so this will be 1 multiplied by 1 plus our Mantissa is small number, so it's 0.6 or something, and we multiply by 2 to the power of -4, and we comment this out. So this would be basically the representation of 0.1, and we can even calculate that. 1 plus 0.6 multiplied by 2 to the power of -4, 0.1. We also have subnormal numbers. That's when the exponent is 0 but Mantissa is not 0. The hidden bit becomes 0, not 1, and the formula becomes something like this. So for our next example, we're going to check why 0.1 plus 0.2 doesn't equal 0.3. Well, actually with faults, we'll see that it does equal, but for example, for 0.3 plus 0.4, it doesn't equal 0.7. But let's check the example anyway. So let's comment these things out as well. So here is the example. Basically, we have these three numbers. We print them to see exactly how big they are. Then we print the result from A plus B. And then on this one, we compare A plus B equals C. And we will either get 0 or 1. 0 if it's not true, 1 if it's true. And here we can see that 0.3, the way we have written it here, is equal to this number, which, as you can see, is equal to this one, which is the summation of A plus B. So in this example, the 14-point numbers are just not precise enough. And that's why here we have 1, which is true. Now let's change it a bit. Let's use, for example, 0.3 and 0.4. It should be 7. And let me just fix these here. And as you can see, with these numbers, the 0.7 here is actually 0.69999 and whatever. But when I sum A and B, I get 0.7000. And that's why the check here is false. The question is, why does that happen? And it's because floating point error is not random, it's deterministic. The rounding error for 0.3 and 0.4 happens to not be exactly 0.7. Not that floating point numbers are broken, they're not. It's a deliberate trade between range and precision. When you use, and for example, here in the assembly, this is where we add the two floating point numbers, and you have to remember that when you use add ss in your assembly, you're not just adding numbers, you are adding binary fractions with 23 bit of precision, then routing to the nearest representable value. And yeah, that's for today's episode. Thanks for watching C++ Under the Microscope. Don't trust the math until you've checked the bits. See you in the next video. Bye.